This is the second lecture of week 10. Let's consider the panel data model, where we have a fatality rate as a dependent variable and beer tax as our variable of interest. Let's say that there's a variable zi that is an omitted variable that doesn't change over time. So for example, the traffic density or the culture toward drinking and driving that doesn't change over time could be considered as some factor. And let's say that this cannot be observed or measured. So for instance, we cannot really measure or observe the culture of drinking and driving. So if we don't include this variable, then this is going to cause omitted variable bias on the coefficient beta 1 that we're interested in measuring. So one of the ways that you can remove this omitted variable is using the differences. And this works when you only have time period of 2. So we'll look at this more closely. So the main idea behind this method is that any changes in the fatality rate from 1982 to 88 cannot be caused by the omitted factor Ci, because Ci by assumption does not change between 82 and 88. So in other words, whenever fatality rate changes from 82 to 88, that is not caused by the omitted factor, because omitted factor is not changing between these time periods. So let's look closely at the math behind this. So here we have a regression for 1988 and 1982, and let's say we subtract one regression from the other. So when you subtract one regression from the other, the intercept actually cancels out, as well as the omitted variable. And what you have left is the differences in dependent variable and differences in independent variables. This regression line can be estimated using OLS. The biggest problem with this method is that it only works when the time period is equal to 2. And it wouldn't work if it's more than 2 time periods. Here we have estimated the coefficients using 1982 data and 1988 data. And as you can see, as you've seen in the previous plot, the coefficient is positive, indicating that there's a positive relationship between beer tax and fatality rate. When you use a difference regression, where you subtract one from the other and estimate the coefficients using OLS, now the coefficient becomes negative, showing the relationship that we think is correct. So the fatality rate and the beer tax now has a negative relationship. When you plot the regression line of the differences, then you get a negative slope or negative relationship between fatality rate and beer taxes. So it shows that higher alcohol taxes leads to lower fatality rate, which is consistent with economic theory. So when you have 2 time periods, you can use differences to get rid of the omitted variable problem. But what if you have more than 2 time periods? We use something called fixed effects in this case, and we can write this regression in 2 different ways. So first, we're going to write it in fixed effects form. So first, let's suppose that we have 3 states: California, Texas, and Massachusetts. Let's say we have some population regression line with the omitted variable that doesn't change over time. So now we want to measure a regression line just for California where I is equal to CA. So your regression line becomes this, and what you can see here is that the slope for all states, all three states remain the same, but what changes for each state is the intercept, and that's because this omitted variable term, z, is different for different states. So we can do the same thing for the Texas. If you want to estimate a regression line for Texas, basically you have this intercept term that is unique, and when you look at the regression line for all three states, what you get is a unique intercept for each state, but your slope beta 1 actually remains consistent. So you can rewrite this regression line in general form. If we were to plot these three regression lines, it would be three lines that are parallel to each other but have different intercepts. And that's because we have the same slope for these three regression lines. Recall that the shift in intercepts can be represented using binary regressors. So in other words, when we have three different regression lines with the same slope but different intercepts, we can represent this in one regression line with binary regressors. So to write these three regression in a binary regressor form, you can include two different dummies. So for example, one dummy would equal to 1 if the state is California and 0 otherwise, and another dummy would equal to 1 when the state is Texas and 0 otherwise. In this regression line, we have to leave out the dummy for Massachusetts, and that's because if we include all three dummies for the three different states, then it will be perfectly collinear to each other, and it will run into multi-collinearity issue. So in this case, we have to leave out one of the dummy variables that represents one of the states. It doesn't have to be Massachusetts, it can be any of the states, but we have to leave out one dummy variable that represents one of the states. So to summarize, there are two different ways to write the fixed effects model. One is n-1 binary regressor form, where we include the binary regressors for the factors that are not changing over time. And another way is to write it in fixed effects form, where in our case, the entity that was not changing over time was state, so we call this state fixed effect or state effect. And the reason why we call fixed effect is because the effect of being in state I is constant over time. So there are three different estimation methods for fixed effect regression: n-1 binary regressor OLS regression, entity domain OLS regression, and changes or differences specification. The problem with the third method is that it only works when there are two time periods. So it's very limited in terms of when you can use it. The first and second method can be used for any number of time periods. The problem with the first method is that when there are a lot of binary regressors, or when n is really large, then it takes forever to estimate this in Stata, so it becomes really impractical. The second method is what we are going to end up using in Stata to estimate the fixed effect. We're first going to start off with the examples of n-1 binary regressor. We have already seen this example of n-1 binary regressors. In the previous example, we created a dummy for the state of California and also a dummy for state of Texas. In this case, you can first create the dummy and then use the stata command regress to regress the dependent variable y on x and all these dummy variables that you want to estimate. The problem with this method is that if you have more than 2 dummy variables are pretty easy to estimate, but say you have 1,000 dummy variables, then this becomes really impractical because it'll take a really long time to first create all these dummy variables and then run this in stata. The last method that we're going to discuss is entity-domain OLS regression. Let's say we start off with the fixed effects regression model and then take the average. So now you have y bar, x bar, and the average of error term. The average of alpha I is alpha I, because if you have multiple alpha I and take an average, it'll be alpha I. You can rearrange this regression model to y bar minus beta 1 x bar minus u bar. And then we can, instead of alpha I in the original regression model, now we plug in y bar minus beta 1 x bar minus u bar, and then what you get is this model, which is a deviation from the averages. When you have this regression model, basically you can say that this is a regression of some y tilde on some x tilde, where y tilde is equal to y minus y average and x minus x average. So for example, what is y minus y average? If I was equal to 1 and t is equal to 1982, then y is the fatality rate in Alabama in 1982, and y bar is the average fatality rate in Alabama in past 7 years. So basically, you're subtracting the average from each data point. So in this method, you need to subtract the average from each data point for both y and x and regress them. This may look very manually tedious, but in stata, this can be done with a single command. How you run this method in stata is that you first need to use this command called xtset, and then put in your entity variable as well as a time variable. So in this case, we have state as an entity and year is our time variable. Once you have told stata that we're using the panel dataset using a stata command xtset, then we can use this another command called xtreg to indicate that we want to do fixed effect regression model. So the command is to use xtreg and dependent variable y and independent variables with the option of fixed effect or FE. You can see that this command gives you coefficient for the main variable of interest, but not for coefficients for state fixed effect that we're measuring. So by default, stata doesn't generate the coefficients for the fixed effects. You can also see that we're using this option to cluster the standard error at the state, and we'll discuss this more in the next lecture. Using the output from stata, we get the coefficient for main variable of interest. And the coefficient indicates that when the beer tax increases, then fatality rate actually decreases, which is consistent with the economic theory. So how many binary regressors would you have included to estimate this using the binary regressor method? So in order to measure the state fixed effects, because there are 48 states, we would have had to create 47 dummy variables or binary regressors to measure the state fixed effects in this case. So that would have been it would have taken much longer time to create 47 dummy variables. When we compare the coefficient from this model to that coefficient from the differences model, we can see that the size slightly differs, and that's because the differences model only uses 2 years of data, whereas our complete model uses the 7 years of data. And another thing to note is that the standard error is slightly smaller when you're using 7 years of data because you have more data, and thus the coefficient is measured more precisely and the standard error is smaller.